Yeah, sorry about the screen issue, but keyboard is not working. HDMI is not mirroring properly. So okay, so once everybody is on Zoom, then I can start walking through a couple of things and then get into the meat of today's session. Is everybody on Zoom? Okay. Okay, so okay, so we'll get started. So we are so first I'm going to deal with logistics. There's no display. So first we're going to deal with logistics. We are on almost the last but one session. Today is 21st, and the next session, next Monday is actually the project presentations. Okay, I think somebody asked for a change of. Yeah, just to mention, just to recap. So in terms of presentation logistics, 8 minutes per group. No explicit time is mentioned in that sheet. That's your order in which you're going to present, except for two teams. You just drop me an email, please, you and her. Okay, that's fine. Okay, we can. That's not an issue. Okay, it's not going to adversely affect anything. So there's going to be 15 teams and 8 minutes per team, according to this, according to the numbers, except for one number which may be off, but you know the sequence. Um, it's going to be 8 minutes of including Q&A. So you wanna, if you want to take less than 8 minutes, you know, that's totally fine. What you want to spend time on is you don't have to necessarily create a slide deck. Okay, so let me get into the specific of what you want to do on those in those eight minutes or whatever 5 minutes. Okay, so you can, in case you did the deployment of a model, it'll be good if you can show your deployment as in like a demo query and so on. That's the minimum, let's say. It's not the minimum, but like that's a good way to at least say, hey, here's I've hosted. It could be local host, it could be on a vendor, AWS or GCP or whatever, or Heroku or something like that. Wherever you've deployed, it's good to have it live during that few minutes when you're presenting. You can use your report itself to do a small walkthrough, but at the same time, don't scroll too much. I mean, you should know, prepare beforehand which sections you're going to spend time on. Scroll to that section and you can discuss your learnings. Okay, so you don't have to make a slide deck. Okay, and within those 8 minutes, both team members ideally should share tasks and discuss. Okay, it's a chance for both of the team members to kind of communicate with the rest of the audience. They're not going to be in person like this, but both of you should take an opportunity to explain your parts of your project. Okay. Okay, now let me ask, are there any questions from anybody about the logistics of the next Monday? Yeah. Yeah, the model itself is irrelevant to us. So whether you run it on Google Colab or somewhere else is probably not important. Yeah, if you want to run the model there, that's fine. But why do you want to show that? I want to show that the timeline is working right. Oh yeah. 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 Do you have any favorite songs so I can switch it? No, I don't, but no, you should ask your friends. But okay, so the question is, can they use Google Colab? Just for the remote audience, by the way. So you can use Google Colab in case it's needed for in your presentation. Okay, so if you wanna briefly mention about your model, you can, if but just focus more on the input outputs and what it does than the details of the model architecture and all that. Okay, if you have done something like that. Okay, so use tools which you think are useful for others to know. Okay, Colab, I think many of you might have used in other courses, so folks know. But if it's relevant to your storyline that you're presenting or in those 5-ish minutes or so, you can certainly do that. Okay. It's basically just think of the presentation as a way to communicate. It's a professional communication. You want to keep it, keep brief, but at the same time contentful, so that people will get value for those 10 minutes or whatever, 5-ish minutes that you are presenting. Okay. And it's just a communication with peers. So you want to focus not so much on technical nitty-gritties but your experiences with whatever MLOps related activity that you did. Okay. Yeah, so that's about the presentation. I want to spend a couple of minutes on the report itself. So any questions about the logistics in the presentation? It's yeah. Yes. Why are you creating a video? It's a live presentation. Oh, you don't have to demonstrate the deployment. If it is deployed, you want to just use the URL in your talk. You don't have to, record the steps of your deployment if that's what you're saying. I mean, it's up to you. Okay, so I don't want to curtail any creativity here, but if you think whatever makes sense in your exposition, you make a choice. Yeah, but it's not needed. Okay, so as you can see, now let's talk about the report. It's actually due on 27th, which is the day before, which is I guess next Sunday. And yeah, I mean, and all these details are there. I mean, I'm just trying to fill up the gaps, and hopefully it's not inconsistent with it's if anything is inconsistent, whatever is written there is the final directions. So there should be basically a zip of your whatever you've done. It could be a deployment, it could be something else like Airflow demonstration, or it could be cron, or it could be other things, right? MLflow related script where you can show that, hey, MLflow, this is how you would track models or something, whatever it is, right? So you should have all the relevant code files. Like for example, if you're doing Docker, there should be a Docker file certainly. And if you're using extra shell commands, then not the commands themselves, but there should be requirements or text, as it says in the notes here. There should be the Python notebooks in case you are showing that you're going to use a request library to make a query to your endpoint. Okay, so just have everything so that if somebody can unzip it and see, hey, I mean, of course they will have to do the deployment, which you have also shown in the report. But if they do the deployment, they should be able to use these extra files to be able to recreate most of it. Okay. If you want, you can include a sample train, feature vector as well as a CSV file if you want. Yeah. If you want, you can add it in your project report. Yeah. Yeah. I mean, if you're going to use some commands, it should be very clear how you're going from step 0 to the scope and then to the end product, whatever you have explored. Okay. So not everything is a deployment. I know most of you may be focusing on the first 3 lectures and so focusing on deployment. But if it's something else like MLflow or A/B testing or something else, it will be slightly different. But I'm just saying that you need to have all the files so that there's no missing step. Okay. So for example, if you want to say, hey, Docker, 2 images of Docker, model 1, model 2, and A/B testing, at least there should be 2 different Docker files which create those images, as part of your submission. You cannot just say I have these models and I've already deployed it, because you can say it, but it's just that we cannot reproduce or check it. Okay, that's all. Just include all the code artifacts, but at the same time, don't submit large data sets or pickle files or other types of serialized files, because it's not needed. Okay, so it's just the code artifacts which are needed, which can be version control essentially. Yeah. So report is 8 pages at most, and there should be sufficient technical depth. And this is where I'm saying that steps should not be missed. That's all. And sufficient technical depth just means that doesn't have to be that you have to be an expert in the technology to talk about all technical details. For example, today we're going to talk about Spark. You don't need to talk about the details of Spark. For example, if you're doing something related to Spark, right? But technical detail just means communication to a team member where they can understand. Given a model, this is what you're doing with the model or the ML workflow. I hope that's clear. I didn't want to confuse anybody, but at the same time, some folks had some questions about format. The example remote components in that project page already mentioned like a few things that you could talk about, like what is the goal, what are some solutions. Like for example, if you're picking up Docker, you may add a comment saying, hey, Docker is one version, there's LXC or Podman or some other implementations that other people can also use for containerization. It's just a comment. I mean, there's not something that you need to know beforehand to be able to add that, but when you're writing a storyline, you may be making decisions while you say, hey, deploy this way, or I'll do A/B testing that way. You want to kind of verbalize those decisions that you're making, even if you don't know the alternative. That's fine, but we are making a decision to do this, do that, and it may make sense in some business environment, may not make sense in other business environments. That's fine. Okay. There's just an exercise, by the way, just an exercise in communicating technical content to your peers. Okay. So it's not for a layperson, it's not for an expert. Your peer who roughly knows machine learning, who roughly knows business analytic tools can understand what's going on. Anything else about the project? Okay, so if not, let's actually get back to our course. I'll switch to the slides in a second, but what we're going to do today is two things. One is, I mean, it's written chapter 6 and chapter 7. Those are the two modules that we'll briefly look at today. Both of them are related to multiple computers. Okay, so I mean, to kind of do the smallest demo, I mean, or not the smallest demo, but in reality, they generally tend to involve multiple nodes or computers. Okay, so chapter 6 is about PySpark or Spark ecosystem, and chapter 7 is about streaming model deployments. Okay? So I want to mention the goals first, and then go talk about the at the high level using slides, like what are these two. Okay, so goal for the Spark component is especially for folks who have done big data, this should be a little bit of a review where they have looked at Spark and Hadoop architectures, right? So the goal is to understand the moving parts of a Spark cluster. Okay, when is Spark cluster useful? Be able to use or at least appreciate the utility of PySpark. Okay, and how do Spark data frames differ from Pandas data frames? Okay, we'll briefly mention these. I mean, we're not going to go into in depth. And we'll also briefly at least communicate that there is this package called MLLib, which is very similar to scikit-learn, for example, which lets you train models also in a distributed way. Okay, so we'll briefly discuss that. Okay, so what we want to achieve through PySpark part of the section is, what is Spark? What's the Spark cluster? What is its utility? What is PySpark? And how does Spark data frames differ from regular data frames? What is MLLib, which is an equivalent, analogous to scikit-learn. And we are not going to cover the last part, which is a managed solution, which is Databricks. Databricks used to be free for like a limited trial, but now you have to register and pay money. So we're going to skip Databricks and do it offline. Okay? But Databricks is a vendor which kind of provides hosted Spark environments hosted on AWS, Azure, and GCP, and so on. Okay, and now Databricks is not the only vendor. There could be other vendors as well. So that's about Spark. The second part of today's session is about streaming model deployments. Okay, so it's not so much about deploying models; it's about understanding the streaming architecture. Okay, so streaming very similar to so it's the core idea is basically that you have asynchronous services or asynchronous units of computation or whatever they're doing. They're all talking to each other and accomplishing some overall data processing task. Okay, so So in that goal, so by the end of kind of talking about streaming, we should be able to understand the difference between a streaming workflow versus a batch workflow. Okay, and we'll look at one streaming software called Apache Kafka. Okay, so there's a managed service called Kinesis or Kinesis by AWS. Okay, that's a equivalent. I mean, it's a slightly different technology, but it's equivalent to Kafka that we're going to see today. Okay, as a small example of what do we mean by streaming setup. Um, and if time permits, we're going to talk about how to use Spark plus streaming, but that's towards the end. Okay, so let me switch to the slide deck. So we are on slide 18. If you directly open the slide deck, or if you're looking at Zoom. So so the utility of Spark is in distributed data processing. Okay, so before I get into the architecture of a Spark cluster, so many times, and you'll see that even in small companies, okay, it doesn't have to be the marquee tech companies or Fortune 500s, even medium-sized companies, they may have, as they evolve and as they do business over years, they would accumulate a lot of data. Okay, and generally this data resides in various industry, notions of things like data lakes and data warehouses. Okay, some of them are well established names here, but so there are these concepts which we'll not get into, but ultimately as an analyst or a data scientist, you will have to touch this data to do some processing. Okay, generally it could be, if you're a data engineer slash data scientist or whatever, ML engineer, you will have to do or even business analyst, you may have to do ETL jobs. Okay, extract, transform, and load jobs. Or you may have to do typical statistical or machine learning type of jobs like imputation, like derived features, maintaining a feature table, for example. Or you would have to do downstream tasks like the usual thing, like building a model, reporting results, retraining the model again and again. So there are all these tasks, and you as an analyst, you would typically be working in a team, and you would not be working on a single machine. Okay, so although you will have an end client, which is your own work laptop, you would not be doing data processing on your laptop. Typically will be connecting to a server, or server typically residing in one of these cloud vendors, and you will be doing processing. Okay? And it could be the same thing, like for example working on Jupyter, but Jupyter is residing on a machine which is more beefy, higher specs. Okay, but even though that remote machine can have higher specs, those specs are may at some point of time may not meet the requirements that you have. For example, if you have, let's say, 10 terabytes of data, then it's not that you can do pandas dot read CSV, or whatever, read from a database. You cannot load that 10 terabytes of data into memory. Okay? Which is like prohibitively expensive. So there'll be a need typically, and this is quite a bit of need, maybe not on the machine learning model development side, but definitely for ETL and data processing, that you typically want to do a data processing which is distributed in nature. Distributed just means like distributed across multiple machines, but so you would need to do that, and folks have developed software which try to mimic from a user point of view as if you're working on a single machine, although behind the scenes everything is happening on multiple machines. Okay, so that's, I guess, a layperson perspective of what does Spark provide, right? Spark is basically a collection of machines with some architecture, and we're going to talk about it in a couple of minutes. But from a user's perspective, they should be able to handle things very similar, like data frames and an unusual SQL type of logic, if you want, for ETL, and also be able to train models. Like for example, think of a random forest model, right? So for random forest model, you have a bunch of trees that you're building. All those trees, for example, do you need all the data to be in the same single physical computer for you to build a random forest model, or can the data lie, different parts of the data lie in different machines, and still you be able to build a random forest model? So behind the scenes, Spark provides, or MLLib actually provides a way to build a random forest model while data resides on multiple machines. Okay, but from user point of view, it's as it's as same or similar to using like a scikit-learn model.fit type of a function call. Okay, so basically distributed systems basically make you feel as if there is a single hard disk, a single memory, a single computer. Okay, whereas behind the scenes there is a lot of things going on. So in this slide, I'm just showing you a figure I got from the Sparks documentation, slide number 19, where it's just showing that there are basically three machines. So you can think of two worker nodes. Node is just a technical term for separate machines. So there are two machines, okay, two worker nodes, okay, and a driver program working on a driver machine. Okay, the three machines here in this example, where via what I call Spark, via Spark context and a cluster manager. These are just terminology and programs part of the Spark solution, which the cluster manager basically manages the distribution of jobs, distribution of data, and distribution of the code that you want to execute, okay, onto the worker nodes. Okay, so if the worker nodes are not present, the driver, if you're running a Python program, and if it's not Spark related, it'll literally run on the driver machine. Okay, so driver machines memory and driver machine CPUs are used for non-Spark parts of your code. If you think of a Python program, and the Spark parts of the, if you're in your Python code in particular, we're going to use PySpark. So let's talk about just Python scripts. So the Spark parts will be actually distributed. Okay, that part will be managed by a Spark context, which talks to context cluster manager, and those parts will be executed on these worker nodes. Okay, so we'll briefly look at use of PySpark today. It's really a quick overview, and if you, most of you might be doing big data or have done big data, so it's hopefully a review for some of you. So the tools that a typical business analyst slash data scientist would use here is, if you're in a Python ecosystem, which is what we've been talking about throughout the course, you will be using PySpark. If you need to build machine learning models, and not just models, but also do unsupervised activities like clustering and so on, you'll use a library like MLLib, okay, and also pandas. If you want to, if you do distributed data processing, eventually, hopefully, the final computation could be maybe summarized. For example, it could be a summary over a year, a summary over whatever, some aggregate statistics, and those can be converted to pandas, and then you can do further processing on the driver machine, or basically non-Spark related. Okay. Databricks is a big vendor in the space because the founders kind of built Spark. So it's a big, it's a vendor which kind of provides Spark as a service basically, and lives on top of AWS and Azure. And so they are, we will not be looking at Databricks today, but we'll try Spark on our own machine that we have on AWS. Okay, so we'll install Spark on our own remote machine and try out PySpark. Okay. So that's about Spark. We'll actually come back to that in a couple of minutes. But next, the second system with multiple computers involves this use case. So I didn't write the system itself, but I wrote streaming and real-time inference. Okay, so real-time inference just means real-time model predictions. Inference is just model predictions. So what is the idea, right? So the idea is shown in this diagram. Again, this is from, I guess, Databricks, the vendor. So what you see in the center is exactly the Spark ecosystem that I was mentioning before. Okay, so except for the word Spark streaming, which I'll mention in a second. So you can see that in the center part, okay, which is what is related to Spark, you can use MLLib for machine learning training, and you can use Spark plus SQL to deal with large data, transform, load, process large data sets. Okay, split across. Now, but it's not like this Spark system operates in isolation. It has to talk to typically, for example, data ingestion from different sources. Like you can see different sources listed on the left side. On left side on the bottom, you can see typical application databases. Okay, like MySQL, Postgres, and typical databases that you might have seen in advanced database management systems as well. And but the new thing is the set of, I guess, names on the top left. Okay, so the top, sorry, left bottom is static data sources, which is typically application databases. So you make a SQL query, get me some columns with some conditions, some joins, and so on. So that's data ingestion. But the left top is a set of what are called brokers. Okay, so these are just brokers, and they broker interaction between different systems. Okay, so and so these brokers act as streaming data sources for your distributed data system. Okay, in this case, Spark system. So so the word streaming data just means that there are further upstream sources which are not shown in this diagram. Like for example, if you pick, let's say, one of the words Kafka on the left top. Okay, Kafka itself is connected to many upstream sources. For example, let's say you're an Android app, okay, for some machine learning plus Android app. Each of the app, which is actually installed on each of the client machines, so maybe hundreds of thousands of users, they all may be sending data to this Kafka service, okay, this broker. And then from the Kafka broker, your distributed data system or anybody else can read information to make predictions. Okay, so that way the broker is kind of intermediary from your actual Android client to the endpoint, which actually makes predictions. So you may say, hey, why do we need this broker? Why can't the clients directly talk to the ML model, which is what like first three lectures were about, right? So directly hitting an ML endpoint and making prediction. The idea is that the idea is about decoupling. Okay? So for example, if for example, the ML model fails, okay, the incoming data keeps getting queued. Okay, so there's this queuing feature of this broker. So so think of the default case in the first three lectures when we did deployment. If your remote server is off, you send a request, you'll get a 404 or whatever, some error, right? So if you're using HTTP protocol, for example, here that's not the case. Okay, so here requests can get queued so that somebody, maybe there's a failover logic, like some sort of a like for example, Kubernetes, which manages containers, can see that a container failed and can respawn the container. Okay, if your container has a ML model, then maybe for some error state and it failed, the container can get back on. Maybe it takes a minute. Till then, those incoming data streams or requests for predictions will not be lost, for example. So that's decoupling. So decoupling and synchronicity that's brought to the system. So that's the value of streaming data sources. And the model itself can make predictions, and that predictions need not be sent directly to the clients. Okay, they can also be sent to the broker, so that the client can make a pull from the broker to say, hey, is the prediction there? If it is there, fetch it, rather than the client also having a server where you make a post request of your prediction. Okay, so what I'm trying to say is that there's a decoupling and a synchronicity that you can bring in via the streaming idea. Okay, it's just an architecture concept of how to engineer your ML system or in general software system. And if you think of all the big typically apps and applications that you see today, for example, Facebook Messenger or WhatsApp or any of these, LinkedIn, they all have behind the scenes these types of brokers which broker between services, and that lets you scale systems. Yeah, so that's why you can see, if you look at the slide number 22, you can see the Kafka on the leftmost side, and also Kafka on the rightmost side as well. So in between this, for example, distributed data processing system like Spark, or it could be something else. It could be as simple as a container, or it could be something else where you're training your model. It could be a single machine, for example. Okay. So any questions about the what a streaming solution, a setup mean? Okay, so I will not talk about the next two slides now. Next three slides now. I will talk about them once we cover Spark. Okay, so okay, so I'm in module 6 or chapter 6, and I want to spend a couple of minutes on just not the code. We want to get to the code and see a simple example of setting up Spark and trying out PySpark based data frames and so on. But before that, I wanted to briefly mention some details about Spark. So, and we have already discussed this just now, which is uh, Spark is a way to um, um, represent a distributed computation from the user's point of view as if it's a single machine computation. Okay, so it lets you run typical data tasks like pre-processing, feature engineering, data training, sorry, model training itself on multiple machines. Okay, behind the scenes. Okay, so all the typical things that you see. There's an idea which, or in fact, a particular terminology that they use, which is the notion of resilient distributed data sets. Okay, RDDs are the building blocks of a Spark cluster. Okay, and we'll not get into the detail of RDD, and we'll see RDD object in when we do a demo in a second. With that, you can actually get scale. Okay, fault tolerance and scale. Fault tolerance is because so scale is exactly what I was talking about. 10 terabytes of data, single machine is not possible, but it's possible on a Spark cluster, and so that's scale. And fault tolerance is exactly because if you keep exactly 1 terabyte of data on 10 machines and they don't overlap, if one machine fails, you kind of lose 1 terabyte of data, right? So you can actually behind the scenes, software can figure out how to maintain resiliency. Okay, so that even if like out of 10 machines or 10 nodes, one node fails, you're from the user's point of view, it's as if nothing changed. Okay, so as the system heals itself. So so that's resiliency. Yeah, so Spark data frames are just containers around these core objects called resilient data RDDs. Okay, resilient distributed data sets. Okay, and they try to the Spark data frame idea. It's like, just think of it as a container, not container, but a wrapper, which kind of tries to mimic all the functionality that you see in a single machine Python package like pandas. Okay, pandas data frame, or even the more interesting ones like Dask. I don't know if people have used Dask. So there are some single machine data frame definitions. Okay, in Python. Of course, there's data frames in R and data frames in other languages as well, but kind of mimic, make it parity wise similar to pandas data frames. Okay. Yeah. So PySpark itself is just a way to. So Spark itself is written in Scala, which is a language targeting the Java virtual machine, and so PySpark is a Python binding to the Spark software. Okay. So and you'll see that we'll have to install Java on the remote machine to get PySpark on our machine in the demo. So yeah. So a brief comment about Spark versus container deployments. Yeah. Spark is a software in Scala, written in Scala. PySpark is it's a glue code which lets you talk to the Scala program. Yeah. Okay. And the Scala program runs not just on one machine, but there's the worker nodes also have that Scala program, and the driver also has a Scala program, within which there's the context manager, which deals with coordination and resiliency and all that. Yeah, data distribution and so on. Yeah, so just think of Spark versus container deployment. So the container was about really about a single machine. So a container can only be an upper bound to a container is exactly the single machine that it can live in. Okay, so in the sense that if you have a 500 gig RAM machine, okay, and that's it, that's the limit of the container. Okay, you cannot go beyond the limitations of a single machine. Whereas distributed data processing, and in particular Spark, you can do more. Okay, so you can do more. So it's not really an apple to apples comparison, because containers, I mean, I'm comparing containers and training, and rather not containers and deployment, because then it will not be an apple to apples comparison. So Spark can also do serving. Okay, so it can be used for ETL jobs, like data processing, I said, as well as training via this MLLib package. MLLib interface, but it can also do serving of models. Okay, and that is via Spark streaming, the acronym that you saw in the slide deck, where it can listen to where it can listen to a broker like Kafka or Amazon Kinesis, and see if there is a request for see if there is a feature vector that came in from which it can make a prediction and send that prediction back to the broker and so on. So in that way, you can actually make a Spark system kind of a deployment, basically an endpoint for making predictions. So what's our goal for the demo sake is just setting up Spark and trying out the data frames. Okay, so it's a very simple exercise, but at the same time, it's you'll see that they made it so simple for us to get started on Spark. Okay, but in business settings, you typically have a team of data engineers or maybe even a managed service provider like Databricks deal with the Spark cluster, and you would be mostly as long as it's hooked up with your data warehouse or data lake, you just run queries or set up your training programs and so on. So that's how it would be in professional settings. Okay, so brief comments about the clusters themselves. As I said, there's multiple machines involved, and we basically submit Spark jobs to cluster for execution. Okay, so as I said, there are so because you need to have a cluster on which a Spark system runs, you can create that cluster yourself. Okay, which is like run the Spark program in different machines, and somehow they discover each other via appropriate networking information and so on. You can use cloud solutions. You can directly use the cloud vendors like AWS or Google Cloud and so on. Or you can use managed vendors. So vendors which sit on top of these cloud vendors, which infrastructure vendors like Databricks. Okay, so these additional service providers, they add more value to just giving you a Spark cluster, which is like they can, for example, Databricks as a vendor, they actually give you a very Jupyter-like interface, so you don't even have to have a separate Jupyter instance running and so on. So they add those types of value adds, sharing of code or versioning of code and things like that. Okay, so those are some advantages, and spinning up and spinning down clusters in case you want to not run a cluster constantly on machines. Okay, so those types of additional value add they give. So what's a cluster? Cluster is just a collection of machines. One machine is designated as a driver, also called, I guess, master, and the other machines are the worker nodes. Okay, workers, and tasks are designed to be distributed across these nodes, and these nodes are susceptible to failure. Okay, so for example, these could be Spot instances from AWS. Spot instances are different from the on-demand instances. Okay, on-demand instances, we are paying a little bit of a premium, so for them to not take back the instance in case somebody else is willing to pay more money. But Spot instances you can get for cheaper, but the risk is that if some other vendor or customer needs that machine, then that machine will be taken away from you. Basically, the CPUs and RAM will be taken away as resources from you and given to them, so you will lose that machine. Okay, so so in that page that you can see here, I'm just showing you. For example, here's a log. This log is actually from Databricks interface, but you can see that the third line in that table snapshot, you can see that nodes lost event happened, which is that the cluster lost one node because of Spot instance, the worker machine getting terminated. Okay, and nonetheless, the cluster still works. Okay, with data not being lost, and you from your perspective, you would not notice that. Okay. Yeah, so let's actually get started with installation of Spark now. So yeah, so let me just directly go to this page, which is on Spark's website. so you can start. You can use this link to install Spark. So there are two things to do: this, and the second link is to install Java. Okay, so you need to have Java runtime environment as well as the Spark program itself. There are multiple ways to install Spark. I mean, using pip, using Conda, or using use the binaries themselves, or compile from source. There are many different ways. Let me briefly mention one issue that that can happen, and that's written in the so that's written here, and this is actually relevant to us, from several lectures ago, which is that if you use pip in a Conda environment, it's feasible, but the approach is discouraged because pip does not interoperate with Conda. Okay, so you can actually see the, I guess, Conda is I guess a tool by a particular vendor, and so they have a page where they say there could be issues that can crop up if you use pip inside Conda. So if you're gonna have a Conda environment, try to use Conda based what is it? I use pip command. Yes. And it was saying it's going to take 6 days or something. It was being cleared. Yeah. Yeah. So yeah, you'll face issues. Yeah. Not everything is available on Conda, right? Yeah, so not everything is available on Conda. Then, so for example, actually even Spark, right? So this Conda Forge is a way to, so -c, I guess, is like for community. So it's not maintained by the, it's basically like external packages which are not, I guess, highly quality controlled like Conda install package. So Conda Forge is letting you, letting probably the community or themselves doing a lightweight integration with Conda, right? But what can you do if something is not available? You can install using PyTorch, except that, sorry, you can install using pip, except that there's some incompatibilities that may crop up. So, okay, so that is not actually a major issue. What you can do is, even with Conda or without Conda, you should always use virtual environments. And we have kind of glossed over that from lecture 1. In lecture 1, in one of the notes, there was this Conda create environment command. So environments are like the self-contained wrappers, again, within which, like if you have 2 projects and they require, one requires PyTorch GPU and another one requires PyTorch CPU, you can install PyTorch on the same machine on different Conda environments, and they will not interfere. And so if you need to kind of mix up pip, then create a Conda environment first, use pip and see what all got messed up. Okay, what changed, for example. You can monitor those things. But yeah, I would say it's not the ideal situation. Yeah. So were folks able to actually, let's see. Actually, Okay. So were people able to install or any issues? So you need both, and then you'll be able to, uh, you know, you'll be able to instantiate Spark through your Jupyter, an example Jupyter notebook. No, you can do, for example, if you so if you're on screen, yeah, you can just yeah, we don't need to do. Sorry, what's your question exact? Ah, okay, environments. Okay, so we are not doing environments here. Okay, so let me actually go back to that page. And so on the installation page, I think you can ignore a creation of a separate environment, but if you want, you can create. If you already started creating an environment, then yeah, conda activate PySpark environment would be useful. No, so all you're trying to do is install uh, PySpark, right? If that doesn't work, so if PySpark installation doesn't work on your default conda environment, like base environment or whatever it is, you can always create a fresh environment so that the reason why PySpark may not be getting installed in your current environment is because we installed so many packages in between, like Torch and Pandas and so on. Maybe the numbers don't match, NumPy and so on. You can always create a fresh environment like what it shows here, create -n environment name. So you can give an environment like name like PySpark underscore environment, and then activate it. And then within that, you can install um, uh, PySpark. Okay. Okay, so I can just show you. So if you look at your Jupyter, right? So here it says, for me, it says data sci dev environment. Okay, so you can type conda list ends to see what all environments I have on this machine. So I have two environments. Oh, no. Okay, this is not correct. Yeah, sorry. So I have two environments, base, and which is what you would get by default. And then I create an environment using that command very similar to PySpark underscore n to create another environment. Environment, just think of this as there's wrappers. It's very similar to the notion of virtual environments. If you have used virtual environments in Python, VN or virtual N. So conda environments are a very similar concept. Okay, so they're you just think of it as if you have three projects with three different teams in your organization. Let's say you're a data science group and you have to work with marketing and some recommendations and something else, sales and finance. So maybe they have different software requirements, and so you can create environments so that they're isolated. They're not leaking into each other. Version numbers are kind of the same, and I say version numbers are appropriate, and so on. Okay, you can do that. So to switch between environments, you just use conda activate environment name, and you can switch between them. Okay, it will take some time. So we can. So in the meantime, also try to install another terminal if possible. Install OpenJDK. Okay, so it doesn't have to be OpenJDK. You can install Java version 8 or even higher versions, but I think version 8 is recommended here. So OpenJDK is just the. In fact, we'll just need the Java runtime environment. It's just the runtime environment. You don't need the tools to build the bytecode from Java programs, okay, or whatever the Scala programs and so on. Okay, so for that you need, by default it doesn't get installed in Ubuntu, so you just need Java runtime environment. Okay, with those two you should be able to run PySpark. Okay, so you'll be able to use PySpark. Sorry. So the way to use it, I'm gonna switch over to a tab. Okay. So once I install PySpark and I install Java, okay, with those two commands that I showed, or the links that I shared in the chat, you should be able to run this. And so this is actually commands I got, which are from the installation page. You'll see a lot of warnings. For now, we'll ignore it. So you should be able to run the command successfully. So okay, so there should not be any error as such. Most of them, all of them will be warnings. Okay. and we can fix them, but I think for the minimal thing that we're trying to do, we will not fix them right now. Okay, so I want to take a second and check anybody facing issues. Okay. Oh, if it's stuck, okay. So if things are not working, then you can also use pip install PySpark. As I said, I mean, there's a disclaimer that PySpark will have issues. Was anybody able to install PySpark successfully? Okay, that's good. No? Oh, you use pip install PySpark? Yeah. But you're not using conda environments anymore, or using Python virtual environments?
I think I use PySpark, so I can use.
Okay.
I tried to put up first and it gave me 2 errors. Was solving environment, it didn't work.
Yeah.
It didn't work, so I just.
Okay. Yeah. Okay. Then I would suggest. Okay, you have it. Okay. That's great. So, folks, I mean, it's a throwaway environment. Actually, if the way we are maintaining our remote machine is not it's just for like training purposes. So, I would say without lots of issues, I guess complication, you can always use pip install PySpark. You want to just get started. Okay. So I'm just going to run a couple of quick examples to kind of show like how Spark is slightly different from Pandas, but also gives you a lot of behind the scenes, right? So the flexibility of having 10 terabytes of data loaded as a data frame is really appealing. And one of the features of Spark or PySpark is lazy execution. Okay, and I guess that's something that folks I don't know if you've used Pandas, and then if you've used Dask. Okay, there's a difference between Pandas and Dask. Dask is also a library that you can install very similar to Pandas, and it gives you data frames, and you can manipulate columns, rename columns, do indexing and all that. The difference between Pandas and Dask, essentially, at least one of the features is lazy execution. Okay, so all the types of processing that you do on a Dask data frame, for example, like renaming columns uh, or any conditional indexing or things like that, they don't get evaluated till you actually call something like a compute, for example, in Dask's case. Similarly, for PySpark's case, uh, PySpark will not compute all the transformations that you are suggesting, like renaming columns or ETL, all sorts of SQL changes like joining and all that. It will not compute it till you want to collect the results and present it to yourself. Okay. So that's lazy execution, and that's a key feature for dealing with not moving data and recreating, or it just is in contrast with eager execution, where you actually execute whenever you run the statement. Okay. So here, whenever the statement is run, generally it doesn't execute the underlying operation, like a join operation or an indexing operation. Okay. So so here we are just seeing an example of a simple data frame, a Spark data frame being created. Okay. So for that, you just need to import PySpark.sql. Okay. From there, you import a row class, and then you can create rows. Okay. So these rows basically constitute the Spark data frame, and you can see the execution here, right? So Spark data frame, really think of that as like a SQL table essentially. Um, uh, and you know that there's interop between pandas, SQL, Spark data frame, and there are many other variations here. So df.show basically kind of actually does the collection compute step I was talking about. So df.show is asking on the driver machine for the user, show me this data frame, which means that Spark has to go back and see, hey, where all is the data present in the nodes, collect them together, compile them together, and show it to us. So just imagine if you're calling df.show, you really need to have enough RAM, which is bigger than the data set that you're processing. Okay, so you don't want to call df.show unnecessarily. Or actually, yeah, df.show or df.collect. Okay, that's the uh, 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 command to collect all the data from the worker machines to get it back into a driver machine where you need to do some processing like plotting and things like that. So the data frame also has some extra attributes like schema is what is going to be interesting. So you need to specify. It's very similar to pandas schema, where you basically say data types for each column that you have. Here you can see the schema for this example data frame, long, double, string, date, and so on. So I'll not, yeah, yeah, and yeah. So you can see different ways to, I mean, when you're creating the data frame, you can create the data frame using the row object, or you can create a data frame from a list of tuples where you specify the schema. Okay, so that's what's going on in cell number 5 that I'm showing in Zoom. And you can also create a Spark data frame from a pandas data frame using, you can just literally same create data frame, sorry, and creating a data frame that way. Okay. And then you can do df to pandas to get back the pandas data frame. Okay, so this is the pandas data frame. And the usual, so df dot, you can see all the typical, it's going to be similar to the type of commands that you can pass to pandas data frames as well. So aggregate, alias, group by, columns, count, typical functions. You can see there are like lots of functions here, a drop, and so on.
So one question.
Yeah.
You can create this Spark data frame from pandas, the one that we just saw.
Yeah. Yeah.
So is it going to convert it into like a distributed data frame?
Yes. Yes.
So how does it know what where to distribute?
So we so that's a good question. I'm trying to see if there's an extra saving that's needed. Yeah, it's a good question. I don't know the answer at the moment. Yeah, I'm trying to remember the right command and I don't remember exactly. Let's see. Yeah, so yeah, I'll have to look up what the right operation does and how is it different from just converting a pandas data frame to a Spark data frame. Yeah, yeah. So generally you want to do this when you have a small enough data frame in pandas that you need to, for example, join or filter. So for example, you may have a small metadata data frame that you have it on a driver, whereas there's a large data set which is distributed. You can convert your metadata data frame into a Spark data frame, then you can just join them using like df.join with the second df and so on. So there are many use cases for doing this, but yeah, good question. Also helps you if you want to not switch between pandas and Spark. You can keep everything in one, typically in Spark because it's distributed. So you can keep all of them. You can convert immediately to Spark. Yeah. Any?
calculate some model. For example, there it is. It can be done in a probability based.
That really depends. Okay, so models in Spark. So think of a random forest model that you want to build on this 10 terabyte data set. How would you even build it, right? So on a single machine, you cannot even load the 10 terabyte data set. You can probably load data set part by part. Okay, that's, for example, even with pandas, you can actually do chunking. Okay, so if your pandas has, if your data has a billion rows, you can load a million rows at a time. Okay, so that so you can load the first million rows, use that for your training. You load the next million rows, use that for training, and that makes sense. For example, if you're doing gradient descent or something like that, you just need a small subset layer to do gradient descent. But it's unclear how to train, for example, SciPy's random forest implementation, or even some other implementations on this large data, right? So you do need the distributed training. So it's really it's providing scale that way, in the sense that you can train a random forest model spread across multiple machines, but is it going to be fast, and can it terminate fast enough? Sorry, is it going to be fast, or whether it's robust and it's actually an in place replacement for scikit-learn's implementations? Answers to both of them is probably no. Okay, from my limited experience. So it may take even for like a depth 30 and like a 10 tree random forest on, let's say, 1 terabyte of data, it may take a lot of time. Yeah. But just the difference is that whatever you couldn't do on a single machine, if you have a cluster and if you really want to build that machine, you can. But there is trade-offs. I mean, it may not be fast. Okay. Because first of all, distributed model training is something that is not universal, in the sense that it may depend on model to model. Okay. The way you distribute a linear regression model and train the linear regression model may be slightly different from the way you distribute a random forest model and train it. Okay. And first of all, for example, if you think of deep learning models, it's unclear how to push each of the like the model architecture to each worker node, assuming that each worker node has a GPU, and do gradient update there, and still be able to like have a consistency and have a global update of the model weights. Okay, so all I'm saying is that there is a lot of I would say it's not at parity with the single machine's use of a PyTorch, or training a deep learning model, or even a shallow model. Yeah, there are gaps. And so if you look at MLLib, I don't know if it's worthwhile opening the page, but I'll not open it. But so Spark ecosystem has MLLib package, which has Python bindings as well. So you can just call random forest, just like how you would call from scikit-learn. You will see that it has only specific implementations. For example, it has random forest, it has logistic regression. It doesn't have some other models that you would think should be there, which are there in, like, for example, scikit-learn. Same thing on the unsupervised learning side. It has a few implementations, because for them, they have figured out how to split across multiple nodes and work. Yeah. Like, for example, if you're fitting a single decision tree, it's unclear how you're going to split, how you're going to make use of data running on different machines and still create the single decision tree. Okay, there has to be some coordination, which is non-trivial. Whereas random forest, there are multiple trees being built, so you can imagine somehow relying on a subset of the data, which random forest anyway already does, but you can imagine how to perhaps it can be split. But yeah, some models are harder. Okay, so I will not okay, I don't want to. So this is how you're join. Like, let df1 is equal to df, and then right. So you join something like this. Okay, so this is something that you would have seen even for pandas. If you're seeing try to do a self join, and you can see that column names have repetitions, so that kind of made the two pandas command fragile. But this is how you join. So you can imagine the typical things that you do: group by, where conditions, order, sorting, and uh, Spark has a very nice way to do SQL. You can express the same SQL ideas using chaining. Okay, so you can call dot group by, dot aggregate, dot the usual things that you see in pandas as well. Okay. Except for the more esoteric SQL commands, most of it you can do it this way. Okay. Yeah. Oh, this is just a copy from I think after you install. I think the next page has. Sorry, this is from the quick start page. Okay. So let me just share it on the Zoom link. So I don't have the file committed on the repository yet, but it's basically exactly the links, exactly the examples that you're seeing here. Okay, and you can see the underlying PySpark data frame is just a wrapper around a what is called an RDD. Okay, so RDD resilient distributed data set. So you can create a resilient distributed data set this way. Okay, so when you create it, it's actually such that when you create these RDDs, they are such that they are actually split across multiple machines if if it's big enough and so on. Okay, and then you can create a data frame kind of wrapper around it by like this. Okay. Right now we've just installed Spark on single machine. It's just a driver, but yeah, so you need to just run Spark on multiple nodes, okay, multiple machines, and make one of them. So in fact, first time you install it, I think it shows there's a Spark config. Okay, so there's an extra config file, and in the config file by default it'll just say this is the only machine. This is the only machine in the cluster available. So it's the driver, and it will also do the same computation. But in the Spark config, you can actually specify where the other machines are on the network. So I'm not talking, I'm not showing all those details. It's beyond the scope. Yeah. Okay. So what we'll do is take a 10-minute break, and next look at Kafka. Okay. So get a feel for this decoupled asynchronicity that I was talking about, and we'll do that right after this break. Okay, so what we're doing now is actually switching topics, but before that, I wanted to briefly mention, especially for projects, one aspect which is actually ignore the spelling mistake here, but one aspect which is to transfer files between your local machine as well as remote machine. There are a couple of ways, and there are actually many more ways. So for on Mac, there's a software called Fetch you can use to transfer files. Okay? So if you have a pickle file of a trained scikit-learn model or something like that, or even a CSV file that is needed on to train something on your remote machine, you can use Fetch as a GUI tool to move data from your server to your local local Mac machine. And on Windows, there's multiple solutions. WinSP, a couple of people have mentioned. So FileZilla is another free tool which can help you transfer files between your server and your local machine, okay, for Windows. So use them as needed for your project. Any questions about this? Okay, so with that, let me close Spark listings. think I. Okay, so so chapter seven's notes are not well organized. I'll fix them after the meeting. Uh, so basically motivate for a few minutes, again, stream processing, and then talk about the Kafka architecture. It's a good exercise to kind of get a little bit of understanding of the slightly different piece of software. The reason we didn't get into detail for Spark is because there's a full course related to big data and such distributed processing systems. So, but streaming is a little bit different. So let's we'll spend a little bit of time on getting to know the basics of it. So um, so in general, stream processing is a big idea. It's an old idea and a big idea in computer science in general. It's a way of architecting system that exploits parallelism. So it's really about the idea of parallelism. It's basically achieved by reducing the dependency or synchronization as requirements between the interacting modules. Okay, so um, it's a way of architecting the system which is very similar to how you do parallel processing on in your own single uh, in Python, for example. There's libraries like joblib or multiprocessing with which you can parallelly execute your functions on let's say you have 10 different data sets unrelated to each other, and you want to train 10 different models. You can do that as long as you have 10 different cores or something like that. You can do that in parallel, right? So that's on single machine, and that's a high degree of parallelism. But not many tasks are like that, right? Some tasks may have somewhere in between a bottleneck which requires sequential computation. Then again, you can parallelize and so on. So those are things that you could do on a single machine. The idea is to kind of emulate or get to that type of parallelism in a distributed setting. Okay. Um, so and if you think of parallelism, which is uh, which is partial, which is not fully parallel, like independent things, and as long as you have enough compute which is all related to each other, unrelated to each other, like multiple cores, you can just parallelly compute things. You have to think about uh, exchanging information between these programs, right? So if they're not embarrassingly parallel, as in like one is not related to the other, one progress process or program or training unrelated to the other, then it's completely parallel. There's nothing to do. But the moment there is partial dependency and so on, there has to be some exchange of information, right? So, and that idea you just carried out to between machines, then there has to be exchange of information between machines, right? So that exchange of machine is the core point. So you really don't think of data at rest. So our perspective is not from hey, data is residing in a data warehouse. Hey, data is residing in an application database. Let's pick it up and make some batch prediction, something like that. So that's not the perspective. Application database, like a MySQL or a Postgres instance itself, is a component in a system where data is always like moving. Okay, so data can move and like keep on getting inserted into an application database. So that's one part. But data is moving, and different services are modifying, augmenting to it, or needing to make predictions and so on. So that's the perspective that you take. Okay. Um, so why do we architect it this way and uh, not not store all the data in an application database first, and then maybe uh, maybe then do processing on it? Okay, and that, or the other extreme where you directly connect um, data source to an endpoint, like the way we were doing in the first three lectures. You can imagine 100,000 Android clients or whatever iOS clients. They all contacting your endpoint on Lambda or EC2 and directly getting predictions. Okay, so that's like a 100,000 to one connection. Okay, if all of the 100,000 require predictions at the same time, 100,000 to one connection, right? So why not architect that way? Okay, so the answer is basically exactly decoupling. So the thing that we're going to introduce in between, like a broker like Kafka, it's a resilient system which deals with failures on either end, deals with latencies, deals with decoupling things. So in case you want to update your model, or in case you want to create two models so that you can alleviate the load on one of the models or endpoints. So you can create two endpoints, and both endpoints can read from the broker the moment they finish the prediction for the previous feature vector. So that way you are alleviating the load. So there's a lot of benefits from doing this type of asynchronous decoupled computation. Um, so yeah, so um, yeah, so let me mention the stream processing platforms. Kafka is just one example that I've been using throughout in the beginning as well as now. There are actually lots, maybe hundreds of stream processing solutions that have been built. And you can imagine the reason why there are hundreds is because every stream problem may have its own idiosyncratic requirements, properties, service level agreements, or whatever, which are different. And then people, come up with their own version of it, to deal with that use case. Okay, so not one stream processing system is not a cure for cure for all these types of problems, these types of properties that you want in the system. Okay, like asynchronicity and decoupling and so on. So uh, so you can see in the example streaming platforms, PubSub is a name for a service, managed service by Google. Kinesis is a name for a managed service by AWS, which are stream processing engines or stream processing, these brokers that I'm talking about. Okay, so where third-party services which have nothing to do with stream processing, one program could be written in Java, one program could be written in Python, one program could be written in Ruby, and they all talk to each other. They all ingest and produce messages or data which can be consumed and processed by other programs, and they all interact through this broker or stream processing engine / platform. Okay, on the open source side, you can see in the second line there's many versions: Apache Flume, Apex, Storm. These are all solutions, some of them actually from leading companies, like Storm is from, I guess, Twitter. Kafka was originally by LinkedIn. And so the big companies which had that level of scale that they wanted and decoupling that they wanted, and they build these systems, and many of them have made it open source. Yeah, so in our context, it's actually just for, we'll kind of limit ourselves to data science pipelines. So data science is mostly the typical use case is the real-time machine learning infrastructure. Okay, so although there are not much notes here, so how does a real-time ML infrastructure differ from what we have been doing so far, where we built a model and clients are sending feature vectors and we're getting predictions? Okay, so that is also real time, because whenever I make a query, I'm getting the prediction back. Okay, but there's a slightly different variant of this problem, which is hard, and that's where you may need these types of solutions, which is when you get a query, okay, from a client machine, the client doesn't have the feature vector. So the client, like think of an Android and iOS phone, okay. I'm doing some activity. Let's say I'm, it's a movie recommendation app, or let's say Netflix or something, and I'm doing some activity. There are some events that are getting generated on my device, and they are gonna go to a, let's say, a machine learning endpoint. Okay, that data is not enough for me to do a prediction of what movies and things to show next. Okay, I actually need the full user engagement history, maybe over the past week or past 30 days or whatever it is, and that data and the recent data together I need to make a prediction, right? And so here you can imagine that you cannot just work with a simple trained model as an endpoint. Okay, you need you need extra components which kind of deal with this real-time availability of the feature vector. Okay, and so maybe the raw data that is being generated from the client, it also needs to be transformed, needs to be processed, needs to be aggregated with the previous engagement data, and that needs to be passed to the model, and the model has to then make a prediction, and that prediction itself may not it's unclear how to like send it back to the client, because client did not make a HTTP request here. Okay, client's data went to somewhere, some intermediate place where it got processed and all that. So there's a lot more moving components in a real-time system. The moment the endpoint is in the moment you're not hitting the endpoint with the full feature vector yourself. Okay, of course you can say, hey, why can't we just maintain the full user engagement history on the client side? That is not easy, because generally you want to have that engagement data in a huge SQL table on your end, so that you can actually do processing and all that and do ETL. So there, these types of considerations is what leads to complexity in the system. Okay. Anyways, that's one big use case for using a Apache Kafka or Kinesis based architecture, okay, for real-time inference. Okay, so real-world examples of companies which use like streaming platforms, and this is just from Kafka's webpage. In fact, let's open it and see what names they have now. So they give a bunch of names, and this is just for this particular implementation of stream platform. If you go to Kinesis website, Kinesis is going to talk about usual suspects, many different vendors or many different companies which use them. So you can see all Adidas, Airbnb, Ancestry, Barclays. Many companies use this. Okay, and they use it for the general purpose software that these companies also develop and sell, right? But and so the same ideas can be used for real-time inference and other things for machine learning purpose. Okay, so that's the special case for us, and that's why we want to get exposed to this stream processing idea. Okay. Yeah, so I think you can see the examples for Zillow and Netflix on Kinesis's website. If they still haven't changed, if they change it, let me know. But those are two examples there. Yeah, so relationship to deployment itself, right? So so there's some, basically what I want to introduce is some terminology, a few bunch of keywords. Okay, so different services on a streaming system, okay, streaming environment, pass messages or data to each other. Okay, so these think of requests or responses. Generally, you call them messages. Okay, so messages are what are passed between producers and consumers. Okay, producers produce messages, or producers produce like feature vector or prediction. They're all product. The services or programs produce those things. Okay, of course, for a program to produce a prediction, it has to consume a message, which is a feature vector, like the ML service, right? So producers produce messages and consumer consumes messages. So a single thing can be both a producer and a consumer, like a ML endpoint could consume the feature vector and produce the prediction, right? So yeah, And so those are the terms to summarize, like messages, producers, and consumers. Okay. And generally we would like to scale, for example, one use case is when we would like to scale the number of prediction models if the number of prediction requests is too high. Okay. So you want to increase the number of these consumers or producers, right? This ML endpoints, if your number of requests is high, and that you can do it using in the stream platform in a very seamless way. You can do that even in a container setting. So remember the notion of like Kubernetes, we did not see it. There you can actually say, hey, from the same image, spin up 2 containers, 3 containers, 10 containers as needed. Like you can change the configuration and immediately. It'll create a replica of the same models which can do inference. Okay. But uh, still there needs to be some sort of some object in the front of it, like a API gateway that we saw with Lambda, so that it can do some load balancing and send the request to these individual containers. Okay. So you can also scale with other technologies. I just want to kind of make that clear that it's not only with producer consumer business that you can have asynchronicity, but you can also have scale, but you can have scale with even regular approaches as well. Okay. Okay, so our goal is to set up a single node cluster. So again, sorry, single node broker. Okay, you'll see that this broker or streaming platform, this Kafka itself runs on a bunch of machines. Okay, why does it have to run a bunch of machines, and why can't it be a single machine? It's exactly because of this, right? So there could be multiple producers, multiple consumers sending a lot of data, sending and consuming, taking a lot of data from this broker, and also the data while it's being shipped from one location to the other also needs to be temporarily stored. Okay, and that storage itself may need replication because of fault tolerance, and may need some clever way of like storing across multiple machines behind the scenes. Okay, so that's why it's a complex piece of software. So Kafka, running a Kafka cluster by yourself, for example, is going to be hard. You typically need a team of engineers to uh, deal with these types of things at scale. Uh, but we'll just do a single node Kafka broker, where what we'll try to do is send some messages to the broker, retrieve the same messages using consumer, and just play around with it. Okay, that's the goal. Um, any questions so far? I mean, what we'll do is next briefly understand the Kafka architecture and then look at the demo. Um, okay, so this is just a hopefully a short enough note, but so Kafka again is written in Java/Scala. It's an open source software. Allows one to stream messages. Okay, and these messages can be strings, can be JSON objects, can be numbers, can be feature vectors, anything, right? So it was developed by LinkedIn in 2011, and since then it's been open sourced, I think in 2014 or something like that. It has, as you can see from this particular node as well as their web page, they claim a lot of features. Okay, so high throughput, lots of producers and consumers hitting the same cluster, scalability. So you can see 1,000, clusters up to 1,000 brokers. Brokers are the individual machines here. Trillions of messages per day. So this is, by the way, this is the type of scale that you would see at like Meta or like any of these social networking apps, or even Google search and things like that. Okay, so or even LinkedIn platform and so on, right? So the broker itself has storage where you can, for example, set a period for which you want to retain data. So although some messages are produced and consumed, message is not immediately deleted. It's persisted in case you want to roll back, and the consumer has to roll back and start seeing the messages from the beginning of time or things like that. Okay, so you can maintain. So that means there is a huge storage requirement for such a machine. High availability, which is exactly like things, even if some brokers fail, some machines fail in the cluster, it will still work. Okay, so that's through the notion of replication of data. Okay, this is the same type of idea that you see in Spark as well. I mean, there are many names, many phrases here, but basically connect almost any producer to any consumer. So the producer and consumer can be written in Scala, or can be written in Python, can be written in C, whatever language. They're bindings to there are packages that you can install. For example, in Python, we'll install a Kafka specific package with which we can talk to a Kafka cluster. Okay. Um, okay. So we will not go into the full technical details, but we'll go into a little bit of technical detail. So um, let's let, okay. Let me just use this page. Um, as I said, there's the notion of producers and consumers. So you can see in this image, um, producers are at the top. There's a box for a Kafka cluster, and there is a bunch of consumers at the bottom. Okay? So there's directed arrows, which means producers produce messages which are sent to the cluster, and the cluster takes these messages and organizes them into producers send messages to actually cluster, but in the cluster they send messages to specific topics. Okay, so topics are very similar to channels or threads. I don't know if you've used Slack or other, like let's say situations. Basically, it's just a email, even an email thread, right? So topic is a is kind of a container within which container is in a wrapper within which the same type of messages go. Okay, so producers actually send messages to topics. Okay, topics are just the level of organization of these types of messages, and topics, which is a collection of messages, now can be put these messages can be put in machine 1, machine 2, machine 3, machine 4, and there's some logic for how to do this so as to be replicable. And consumers consume from topics. So topics, just think of it as if let's say it's like like three producers want to talk to three consumers, but producer one only wants to talk to consumer one. Okay, then there's going to be one topic dedicated to them, for example. As it says in the note, messages can be read multiple times because of persistence of the messages. So many consumers can read the same message, for example. And the management of topics, partitions, and messages, okay, happens on brokers, which is essentially like the unit, the actual underlying physical machine node of the cluster. Okay, so partitions, for example, are copied and synced on multiple machines for redundancy, as I was saying. Um, so let's actually, will not follow exactly this note, but let me come back to our slide deck. Okay. So this, I want to motivate this slide, but this is basically just showing where Kafka fits in. So I don't want to talk about all the elements in this slide deck, but you can see that Kafka is there in the second row, where Kafka feeds into a data lake and then feeds into a Databricks or whatever Spark system and so on. Okay. Let's actually look at this figure here. So as I said, the cluster itself uh, talks to many different softwares. It can talk to a database. So for example, as I said, Kafka can store data, but it's not a storage solution. Okay. So eventually there has to be a consumer, for example, a consumer which kind of talks to Kafka, gets all the messages and dumps it to an application database or a data warehouse or whatever data lake. And Kafka is connected to stream process like apps, for example, machine learning endpoint, a Databricks Spark streaming endpoint, and in general apps like actually clients of client devices of your app, for example, right? So before I get into like a demo for Kafka, I want to briefly show how the partitions themselves work. So I don't know if it's very useful here. Yeah. So on the left side, on the left side is the same figure as before, but on the right side, you can see there's it's called anatomy of a topic, right? So what we're trying to show is that there is a time, there is a number associated with each message essentially. Okay. So the number will always be in order in the partition. Okay, so you can see in partition 0, there's number up to 9. Sorry, the yeah. So the numbers will always be in order. Okay, so there's some in order relationship that's maintained. That makes sense. That actually helps. Earlier, I said a consumer can read from some earlier point in time. Okay, that's not easy to do if messages are like jumbled up and stored. It can basically, it's a rewind operation you can do, and you want to store information appropriately. Okay. But if you try to read, and it turns out that in Kafka, if you try to read messages across partitions, you cannot know the order relationship. But if you read messages from the same partition, you can actually get the order. Okay. So for example, if you're getting data from a single client, try to store it in a single partition. Okay. Partition itself is replicated, by the way. Could be 3 copies of the partition. But if you're getting from one client, keep it in the same partition. From another client, keep it in the same partition, so that if you need to rewind for that person, or sorry, that client, that whatever sent the data, you can do that in Kafka. Okay, that's one minor thing I want to point out. Okay, let's actually come back to our setup. So okay, here I'm just showing how to set up on a different vendor, but let's actually come back to yeah. So okay, so we can go to Kafka's website. So okay, so you can install any one of these. So we can install Scala 2.12 or 2.13. Okay, so I'm just going to copy the link and download it in our cluster, sorry, in our remote machine. Oh, actually, that's not correct. Okay, so I just downloaded the Kafka zip or the precompiled. Oh no, I downloaded the source. Let me come back to. Okay, and then I'm just gonna unzip it or basically untar it. So okay, so you should be able to see this folder. Okay, can't see it here, but Kafka 2.13 and so on. And then let's see if we can follow. Actually, we'll need many terminals, but I think um, since we have multiple terminals, we can go along. So let me just check Ben. Yeah. So we are just so what we are starting is an auxiliary program that's needed to run Kafka. So let's run this. I mean, you can see some choices like number of partitions is one, and things like that. So it's basically saying there's only one partition here. Um, yeah, actually, I did not see the heap size. Let's see if it works. No, I need to edit. Huh. I'm trying to figure out where the heap size setting can be changed. No, that's not correct. Okay. 512 MB. Okay, so I think you can see from the Zoom session that I just had to change the heap size to something small. Heap size is a property for the Java virtual machine. Um, so just think of it as like, in general, Kafka needs a lot more resources, certainly not a single machine installation, but for us, um, we we have started what is called Zookeeper and Kafka. There are two. Zookeeper is a auxiliary program. It's actually not needed, but for this demo, start Zookeeper first and then start Kafka like this. And then let's, yeah, so then we can actually start creating topics and um, uh, look at this way of sending messages to Kafka and retrieving messages from Kafka. So actually, let me see if I have a example. It's not working. Okay, I think the heap size was a bad choice. It's hung my machine right now. Um, okay, okay. Let me just show you locally at least, because that machine is not responding. So So what we need to install is a Kafka package, okay, and import it this way. So from Confluent underscore Kafka, import a producer or a consumer. Okay, so you can create a topic, from the command line on the server like this. Okay, so you're just saying Kafka server. Sorry, not that one. So create topic. We're just calling it quick start events, and these are some default parameters that you need to pass in. Okay, so you can call it quick start events, you can call it some other names, but once you create a topic, then you can just use um, producer example and consumer example to send messages to this Kafka installation. Okay, so it's all local host, so that's why I'm calling it as localhost some IP address. Okay, so create a producer object. Okay, and then produce a topic. So producer.produce to a topic, whatever it's called, quick start events or MLOps topic or whatever you want to call it. Send a key comma value. Okay, so you can do that. And similarly on the consumer side, you just have to create a consumer object. Again, configuration just captures which server you want to which Kafka setting machine you want to connect to, and then you just subscribe to the appropriate topic, and then you can poll from that topic. If there is a message, send me a message. If there's a message, send me a message. So you can poll and see what messages are there. Okay, so um, you can see that message. The message that you see here is the message that was sent here. I'm just showing it to you locally, so that two Python files which are both talking to this intermediate program. One is sending a few messages, like producer local is sending these 3 messages, and consumer is able to retrieve. Here it's only able to retrieve the last message, but it can actually retrieve all messages in sequence, again and again. And also producer and consumer, just think of them as proxies for your actual users who want the predictions, and consumers to be where producers to be the people who want your predictions, and consumers to be the ones who generate predictions, who themselves will be producers later on once they generate the predictions. But and so you can imagine, if your ML deployment fails or the ML endpoint fails, producers can keep producing those feature vectors for which they want predictions. Okay, that'll get buffered at the Kafka broker, and once you restart your ML endpoint, it'll start reading those messages from last time it's crashed or from the beginning, and keep making predictions. Okay, and those predictions can again be pushed into another topic, like predictions topic, and then they can be picked up by the appropriate end clients. Okay. Sorry, I mean, so the demo did not work because the machine is I didn't choose a small enough. I should have chosen even a smaller heap size. Um, okay, so with that, let me just conclude. Yeah. So the tools for this part, at least the streaming part, is just Apache Kafka. Just download the binary and run it, and run Zookeeper and Kafka. We saw the 2 commands earlier. So as I said, in general, at least small companies, they will not generally run their own Kafka cluster. They will use a managed service by something like AWS or GCP, like Amazon Kinesis or something like that. Okay, and yeah, so if you have time, try to run it. I mean, you can run Kafka locally. I don't want to take time to run it locally, but if you run it locally, you'll be able to see the publishing and subscribing, publishing and consuming operation with Python programs, or even via using other, it doesn't have Python programs which talk to this Kafka machine. It could be also a different program in a different language that can also talk to the same Kafka program. Okay, so anyway, let me round up because we have like 2 minutes. So what have we seen in this course, right? A very short course with only like 6 or 7 lectures. We started with batch machine learning, model deployment. Okay, so we don't really spend time on the model quality or the model training itself. We looked at basically 3 types of deployments. One is, literally you owning the web server and everything in that stack. So spinning up a server, a bare metal machine, setting up its security, setting up the packages, and then literally launching a web server there. Flask is not a production server. Okay, so there generally is an extra layer that you add on top of Flask, like Unicorn or GUnicorn and so on. Okay, so which we have not seen, but that's one way. The other end of the spectrum is serverless, where you only focus on your script and nothing else. Kind of runtime is given to you. Of course, you need to install the requirements, in case you depend on pandas and numpy and so on. You need those things. And in between is the Docker way, where you have your script and you have a Docker file, you create an image, and then you ship it off to an appropriate location wherever you want to deploy it. Okay. So of course, there has to be an appropriate Docker daemon there, which can interpret and read the image and create a container of it. But once you containerize, you can actually replicate, and you can. There's a lot of flexibility that comes with that. Okay. The second set of things that we saw is model testing, A/B testing using planout is one example. It's the simplest package. That's why I used it. Written by a Facebook researcher, but there are many managed service vendors who do this. Optimizely is one of them. So A/B testing is a big part of many companies these days. Model versioning using MLflow. It's a very easy to use tool. MLflow is integrated, for example, with Databricks as well to version control your models. And then we saw Airflow and cron. Okay, cron just to schedule some simple task in a single machine. Airflow, we didn't see multiple machine thing, but Airflow is a more feature rich setup. Okay, it's Python based, and so fits with the Python based things that we've seen. And today we saw Spark and Kafka. Spark is for behind the scenes doing computation, data processing, ETL, model training on multiple machines, whereas from the user perspective, it seems as if a single machine. And then streaming infrastructure, the biggest use case is real-time machine learning, where client cannot send a full feature vector to you for you to make predictions. You need some other data, and so the protocol is not a simple HTTP get request or a post request. Okay, and so there you can use this message broker to intermediate between a publisher and a consumer, and so we didn't see the demo for Kafka, but so that's where we are. But those were just a very few sample of technologies. In the exercise pages of our repository, there are many links to other technologies, Heroku or SageMaker or Streamlit, or these types of things that you can use for quick use for as a business analyst / data scientist. Okay. Anyway, so next steps. As I said, simple solutions work. When they work, you should use it. So while making decisions, don't just focus on latest and greatest technologies, but also just suitability of the technology for the application. So the quote here says, you can build a crazy deep learning model and put it on Kubernetes on a multi-cloud situation, but you may just need a SQL and an application database and a simple logic regression model. And you do one in the production, the other one in your resume. So just a caveat that you need to pick the tools, right tools for the job. Anyway, so with that, I'm ending this. Was it? Oh, it's called GUnicorn or Unicorn. So what they do is they deal with their intermediary between talking to a Python process and talking to the port where the requests come in. Okay. So the Python process itself, talking to directly fielding requests is inefficient. Yeah. Yeah. That's not enough for scale. I mean, yeah, that's enough for us to quickly demo a Flask with like 10 requests per minute or something like that. But the moment you have like 100 requests per second or even 1,000 requests per second, you need this one extra layer. Okay. Like if you're deploying on Heroku, it will show you on the Heroku's tutorial to have this GUnicorn or there are others. Okay, they're called WSGIs. Okay, Web Server Gateway Interfaces. Okay. I mean, I didn't want to get into that now, but okay. So I guess that's it for today.